No weather problems today, so it looks like we'll be okay. Of course, I just said famous last words. There we go. So I've got lecture 5 up here. The first part of it is a little bit of review, and then we have a few new concepts. So putting predictors together into the same model. Here we go. Maybe. Slideshow. There we go. There we go. That's what I wanted to do. All right, can you all see my screen? Hear me? We're good to go? Okay, all right, away we go. So what we've talked about so far. The role of each predictor variable in creating a custom outcome can happen through one or more slopes. So the very first things that we did in terms of modeling, example 3, homework 3, had a predictor variable whose relationship with an outcome is captured by just one slope. So for instance, if all you have is a linear effect of a quantitative predictor, like having the number of pleases predict the number of fits, for instance, in homework 3, you have one slope, and that's sufficient. Likewise, if you have a binary predictor, so something where there's only two groups, those two groups have only one difference between them. The one slope captures that difference, and that's all you need. If you have a quantitative predictor that has a nonlinear relationship, such as a quadratic effect, then it takes two slopes to be able to capture that curvilinear association. So you would have the linear effect, say, of enthusiasm for mini golf, as well as enthusiasm times enthusiasm, which creates a quadratic effect, and they work together to create some sort of curvilinear trajectory. Another instance in which it would take more than one slope to describe the effect of a single predictor variable is if your predictor has 3 or more groups. So if I have 3 groups, that takes 2 slopes to differentiate the 3 group means. If I have 4 groups, it takes 3 slopes. If I have 5 groups, it takes 4 slopes, and so on. And so the model in that case will give you some of the group differences, the ones that are relative to the reference group, and the others can be obtained as linear combinations. And so you guys have had practice doing that. For each slope that you get, we would have an estimate. So that's always the first column on the output. It's labeled as coefficient, I believe, in Stata, and estimate in SAS. Those terms are synonymous. That gives us our best guess as to what the slope value would be given your data. Next column over is standard error, and that conveys how far off, on average, your sample slope would be from the population slope. So it's a measure of imprecision. Standard errors are greater if there is more residual variability in the outcome and if there are fewer people. Those are the things that go into it. Next column over is your test statistic, the thing that allows you to then map this result onto some sort of standardized metric, like a t-distribution in this case. It tells you whether or not your slope value would be sufficiently unexpected relative to an expected slope of 0. So if your null hypothesis slope is 0, you can look at the t-value for what your slope is, and that can give you a sense of how unexpected it would be. Let me see here, my computer's making blinking noises at me. Am I frozen yet? Not yet, okay. I think I need to shut off Dropbox, that's memory hog. Okay, there we go. Hopefully that'll make it better. T-test statistic, next column over is your p-value. And so that is the probability of observing a slope that you found if the true slope in the population were 0. And so that's where the dividing line of expected versus unexpected is. A p-value of p less than 0.05 means less than 5% of the time you would see a slope that big if the true slope were 0. So we declare that sufficiently unexpected or significant. If p is greater than or equal to 0.05, we would declare that not significant, which means sufficiently expected. So it's not differentiable from just noise, so to speak. All of that so far tells you whether or not you have an association between a predictor variable and an outcome, the direction of the association. So if it's positive, that means as x goes up, y goes up. If it's negative, as x goes up, y goes down. And whether or not it's significant, one more piece of information that you would want to provide is an effect size that tells you the absolute strength of the effect that is not contaminated by sample size. So if I have a significant result, it could be because I have a really strong relationship, or because I have a lot of people, or some combination thereof. So effect size takes the number of people out of the equation and gives you a value that describes the strength of the association. And so the two effect size metrics that you know so far, there's the R family for correlation, where 0 means no effect and -1 or +1 would be the biggest ones. Then there's also the D family, which is standardized mean differences. And so either of those can be used. You can convert T into those. There's formulas to do that, and I've done that in your examples as well. In general linear models, the R can also be found as a standardized slope. And so that's what you get in Stata if you add on the regress line the beta option after the list of predictors and the comma, or using proc-reg for regression in SAS. The reason we're not using proc-reg all the time is that it has less flexibility to do other things such as estimate statements. It doesn't have those. So, okay, so that's slide 2. How are we doing so far? Does this all sound familiar? Reasonably so? A little bit? Practice makes perfect. I have a new hack today. I've stuck a straw in my Diet Mountain Dew can because I can't get the can near my face with my microphone in the way. So I've hacked it a little. Good. Okay. I once had a dentist tell me to do this all the time to try to keep all of the acid from the soda off my teeth. I was like, no, I don't think that's going to happen. But little did I know, quarantine, people get resourceful. And since none of us can visit a dentist, it's probably important to sip out of the straw. So, anywho, so in terms of model coefficients and what they mean, more review here. So if I have a single predictor here, I have x1 as my single predictor. So just to review the notation system, y with a subscript of I is the original outcome variable. It gets an I because each individual has a different outcome. X1 is the predictor here. It also gets an I for the same reason. Each person has their own. The model parameters, the things that we're asking to be estimated in this model, are beta 0 and beta 1. Beta 0 is the intercept. Beta 1 is the slope of x1. The intercept is always the expected outcome when your predictors are 0. So that would be whenever x1 is 0, which is why we center our predictors if 0 doesn't mean something so that the intercept makes sense. And beta 1 tells us the effect of a 1 unit change in x on y. So for every additional unit x, beta 1 is what changes in y. And so if beta 1 is positive, that means y goes up if x goes up. If beta 1 is negative, then y goes down as x goes up. And last but not least, the e at the end also gets an I because each person has one. That's our residual, or error, as it were. That's what E stands for. That is the difference between the outcome that is predicted for you by the model, so by x1 in this case, and the real one. And we don't really care what the E is for each person. What we care about is its variance across people. So we take each person's E, we square it, we sum that up across people, we divide by the denominator degrees of freedom, sample size minus the number of effects we had to estimate, so it would be 2 here, and that gives us error variance. So we want to see that after putting predictors into a model, that error variance reduces in size. If we wanted to provide an effect size for this relationship, the standardized slope, so beta 1 that you would get if these predictors were all z-scored so that they were at mean 0, standard deviation 1, standardized slope would be the exact same thing as Pearson's correlation in this case, because there's only one predictor in the model, and we're saying that it has a linear relationship. If I had a different predictor, x2, then everything follows exactly the same way, except that now I have beta 2, which I have labeled to be consistent, which tells me the effect of x2 in predicting y. And so beta 0 is still the intercept. It's still the expected outcome when the predictors are 0, but now it's conditional on a different predictor when x2 is 0 in this case. And beta 2 tells us what happens to y for every unit change in x2 instead of x1. Then everything else is the same. So what happens if we were to try to put them together? As that's the new part. Okay, who's talking? Or no one wanted to talk? Just an accidental microphone bump? Would anyone like to talk? No, we're good so far? Good? 2 thumbs up. I've already had my allotment of caffeine today, in case you couldn't tell. That's why I have the placebo dew, as it's known. This is the control group Mountain Dew. Tastes the same. Chat window, yada, yada, yada. Yes, that is a Seinfeld reference. Is that correct? Okay. Yes, you are my people. You get my cultural references and I get yours. All right. So in terms of testing multiple slopes at the same time, to be able to say whether or not the model works to be able to predict an outcome. If we have more than one slope in the model, we can't just look at the significance value for each slope. We also need to consider how they work together. So that's where our friend F comes in. And F is a ratio of the amount of information captured by the model per slope it took to get that information, relative to the amount of information left over per slope you could have had but didn't. So it boils down to what you know over what you don't, with a weighting system in process based on how many slopes it took to find out that information. And so that tells us if the slopes work together to create a predicted outcome that is significantly related to the real one. So if I made a column in the data set of everybody's predicted outcome from my model, and I correlated that column with the real outcome, I would get an R value for that correlation. If I square that R value, that is my model's R square. That describes either the squared correlation between the Y predicted by the model and the real one, or proportion variance accounted for. So if R square is 0.1, that would mean that 10% of the original variability in my outcome was explained by my model. And we want R squared to be as high as possible. In real data, it doesn't get that high oftentimes. If you only had one slope in the model, you wouldn't need to consider F or R squared per se, because F would be the same thing as the t squared for that individual slope. So if there's one slope, then the slope is the model, and t and F are giving you the exact same information. Likewise, if there's one slope, the slope's effect size R squared is the same thing as R squared. So there's a one-to-one correspondence, which is why we didn't start talking about F and R squared until example 4 and homework 4, when you had a chance to practice having models with more than one slope. So all of that stays exactly the same. We're just adding one more concept to what you already know that describes what's going to happen to these values when you have more than one predictor in the model at the same time, more than one conceptual predictor. And there is a shift in language that people use to describe the effects of these predictors when they're in the same model at the same time. It goes from what people would call bivariate, meaning just the relationship of one variable with another, to unique. What is the relationship between one variable and an outcome after considering other variables? So that's the new idea. And so we have the same procedures for testing the slopes, but what they mean is a little bit different. And we have a different, we expand our procedures to consider what happens when we add more than one predictor to the model. And so I'll give you a chance to practice all of that in homework 5 if you'd like to do so. So this part of the story gets mathy real quick. So before I get all mathy on you, can I make up that word? Statty, mathy? Yeah, it is. It's more mathy, actually. I want to give you sort of a conceptual version of what this is going to be about, and I would like to borrow the cast of This Is Us to do it. Does anyone else love this show? Anyone? Just me? Okay, thank you, Alexis. You like the show? Thumbs up. Carly likes this show. Okay, there's always a few people. I know people who like it. Who? Uh, I would say older women tend to like this show. People like my mom. It started to drag on. Yeah, they've introduced a lot of new characters. I get sort of confused trying to keep track of like whose life we're in. But anyway, I still like the show. I'm still going to watch it when it comes back. But for those of you who are not familiar, the cast of This Is Us is there. This was us, seriously? Okay, that's more than I needed to know. So the story follows one family that has a mom and a dad and three kids, and the the story happens during different points in their life. So where it started, we were introduced to the grown-up versions of the children, and but then we watched them in sort of previous clips, so to speak, of what it was like when they were babies and when they were teenagers here in this picture. And now we're meeting their children in the future, and it's like this whole long thing. But we'll just focus on the children here who are teenagers. So we have Randall here, we have Kate, we have Kevin, um, and then we have Rebecca is the mom who's always looks perfect no matter what, and of course the dad Jack. So let's say hypothetically that in the Pearson household with the three messy teenagers, that Rebecca has had it with the mess and they have to do something about it. So let's say that the house has 9 rooms that are potentially cleanable. Each of them has their own bedroom, 2 bathrooms, 1 living room, a kitchen, and a dining area. So she decides to incentivize them cleaning up the house and sets the rule that for each person who is not her, so the husband and the 3 kids, that anybody who cleans a room all by themselves gets a new Nintendo game. Because when they were this age, that would have been back when Nintendo was a thing for the first time. I know Switch has come back. My son is addicted to Animal Crossing. I do not understand why. If any of you play that game, I don't get it, but it keeps him occupied for hours, and that part I enjoy. But Nintendo was a thing back when Super Mario Brothers and Zelda and all of that, like this is the era we were talking about. So that would have been a very good incentive to clean, because Nintendo games even back then were like $50 or something. That's a lot of money to save up for allowance. So she also offers a bonus though. If more than 8 or more rooms in the house get cleaned, then the whole family gets a TV. So there's an extra prize for working together. So this is the system we're setting up. So Rebecca goes off shopping. She lets them divvy up what they're going to do with for themselves. And she comes home to a clean house. And now we get to figure out who gets to have what prize. So here's a chart for what happened in this example. Let's say that come back. All the 9 rooms are clean, so the family gets a new TV. The joint prize has been held. But how many Nintendo games should each person get? Well, we have Jack claiming that he cleaned the master bedroom as well as the kitchen and the dining area. And we have Kevin claiming that he cleaned his bedroom and the living room. And Kate says she cleaned her room and the living room. And Randall, of course, is the overachiever of the family. He tried to clean everything and ran out of time. Because that's Randall. That's what he does. But how do we know like who actually cleaned the living room? Because all 3 of them claimed that they did it. So, and likewise for the kitchen and the dining room. So what's going to happen is that each person should only really get credit for the room that they cleaned that no one else said they did. That's the only fair way to solve this problem. So Jack, Kevin, and Kate each get 1 game, and Randall gets 3 because he did 3 rooms. Okay. So this sort of system of how do we give each person credit for their effort, we have to consider what is unique effort, because that actually makes a difference, and what is common effort that we would have difficulty attributing cause. So in this case, no one gets credit for these rooms down here. They got clean, but we don't know for sure who is responsible, and so no one gets a new Nintendo game based on this. So this is my way of explaining the idea of what happens in these models when you start putting more than one predictor in at the same time and those predictors themselves are related to each other. So if x1 predicts y and x2 predicts y, but x1 and x2 are partially have the same information, if they're related to each other, it gets hard to figure out how much of what happened in the model is due to x1 versus x2 versus the part that they have in common. So when we have more than one predictor, we have to be able to divvy up in the same way as in the Nintendo games, who is responsible for what. And so we still want to know on the whole how good the model is, meaning what is my R square? Like how good of a quality of prediction did it take? And that R square is going to reflect both the unique effect of each variable that any other variable doesn't have and the common parts between them, because common still contributes to prediction. It's just that common isn't going to be attributed to any one predictor. So what is the unique contribution of each predictor to the R square after discounting or controlling for its redundancy? And this sort of diagram here, it's either called a Venn diagram or a Ballantine. Have you seen this sort of picture before? Yeah, this gets used to explain a lot of concepts. If we have y right here as this circle, and we have x1 as one predictor and x2 as another predictor, then this diagram is used to show C right here. C is related to y and x1 and x2, but C is the part that we wouldn't be able to give credit, so to speak, to either x1 or x2 uniquely because they both share it. So A is the part that x1 has in common with y that it doesn't have in common with x2. A is the unique part of the association between x1 and y. Likewise, B is the unique part of the association between x2 and y. So in terms of judging how good each predictor is, x1 is only going to have the A part in that. x2 is only going to have the B part. Neither one gets credit for the C part, but the C part does contribute to the R square. And then math. So before math, how are we doing? So we have, I think, let's see, who was it? I think it was Melissa. I'm calling on you, Melissa. You had an example that you gave several weeks ago about this sort of question, right? And you're working on, if I can share about can I tell them about your project? Okay, so she's looking, or do you want to tell them? Okay, here's my memory of the emails you sent me. You want to look at whether or not the size of a school, so levels of rural versus urbanness, is associated with the availability of math at the high school level. And theoretically, less urban schools maybe have fewer options. And if you don't have enough math classes in high school, then you have to take more math classes in college to get all your prerequisites to get to college math, and that's not good, right? Is that's the gist of it? Okay. So in looking at trying to predict how many extra math classes you'd have to take in college, you could look at whether or not that is predicted by the type of school you went to. But then you also would want to consider how many math classes the school had. So those things are related to each other, and if they are, then it's hard to tease apart which variable is responsible for which thing. So phrased differently, is it advantageous to go to a bigger school, even after factoring in the fact that the bigger school has more math classes? Or is it really just the bigger school has more math classes and that's why it matters that you went to a big school in terms of how many math classes you have to take? Or are there extra advantages that we don't know about? So to what extent does one predictor still matter after considering something else that's related to it? Things like, is smoking bad for you? Is smoking bad for your unborn child? Probably. And so in studying the effects of babies who were exposed to nicotine, one of the things that people always want to control for is, okay, well, what is it that smoking entails? Smoking is not just the physical smoking, but there's who is more likely to still be a smoker, right? Smoking is related to socioeconomic status. So you would want to try and piece apart, if you see deficits in a child of a smoker, is it because of the smoke, or is it because of the type of household that that child is from? Do they not have the advantages that other children would have, for instance? And so trying to pull those things apart in the real world, these a lot of research questions are phrased that way. Does something still matter after controlling for something else, or is it just that? Looking at, say, the progression of women in science. Does it depend on how many children they've had or what other opportunities that they've had? Are there things that can explain the gender gap, so to speak? Is gender a proxy for other things that isn't just gender? So lots of real world examples there. Can you think of any others, those of you who are working on data projects? No. I bet you can think of them in your head though, right? These sorts of questions. So I have all the stuff in here for the background in terms of how this works. But the bottom line is that each slope, once you combine multiple predictors in a model, each slope reflects its unique contribution. That's what you need to know. The common part, that the things that slopes, the variables that are predictors that have in common, the common part is not attributed to any one slope. It is in the R-square though. So if we have a model that looks like this, here's our one predictor model. The effect size that you would get for that one predictor is the same thing as the Pearson correlation. That is no longer going to be true if you have more than one slope. The standardized effect for a given slope here is whatever the relationship between that variable and the outcome would be, but then you have to subtract off this part in parentheses that refers to the common part. So everything gets corrected, so to speak, for what covariance is in common between two predictor variables or more than two predictor variables, and the slopes reflect that. Let's see here. Yeah. So we need a different kind of effect size to describe a predictor's unique effect on an outcome. There's many different ways to do it. One that you haven't seen yet that you may come across is something that's known as a semi-partial correlation. Has anyone had this before? Maybe? Sounds vaguely familiar? Yeah, not to be confusing, but there is such a thing as a partial correlation and a semi-partial correlation, and those are not synonyms. But a semi-partial correlation is the same thing as a part correlation. So you may hear it phrased that way. Question: can you change your cursor size color? Make it bigger? That's Carly, right? Sorry, I didn't see you. You want me to make it bigger? Try and do that? I can try. Give me oh, I can't minimize the window while I'm sharing. It's what? I'm sorry? Okay. It is pink. So can you see it now? Does that make it better? Okay. I'll try to keep it active in that case. So semi-partial correlation is, it reflects the contribution of that variable, that predictor, to the model that no other predictor makes. So it's the unique contribution. There are many different ways to calculate them. One of the reasons why people like to refer to them is that they map directly onto the variable's contribution to R-square. So of all of the variability that is accounted for by the model, what piece of that came from each predictor is given by a semi-partial correlation, the squared version, since R-square is squared. So here are all of the various ways you can get that. I will show you how to get that out of software, obviously, because we're not doing hand calculations still. One thing that is sometimes not understood as well is what happens to the common variance. So if you have two predictors that are highly related, you can put them in the model together and neither one of them looks like they contribute. And my stream is disconnecting and now it's coming back. Okay, yep. No, I'm not singing Frozen. If you want to sing Frozen. Oh, Cheryl, your dog is learning with you? That's very cute. Excellent. All right, we're back. So language that goes along with these ideas. If I have this model where x1 and x2 are in at the same time, check recording. Yes, thank you for the prompt. Okay, it says it's still screaming. Yeah, I was all freaked out about that on Tuesday since I lost the stream for a minute. And then for my second class, totally forgot to turn it on. Didn't even start it. Yep. It's like, okay, well, I guess if you're not here. But yes, the stream is still recording. We're still in good shape. Okay, so if you have both variables in the model at the same time, x1 and x2, so this is the first time we've seen something like this where x1 and x2 are different ideas, then the intercept, always the same, expected outcome when the predictors are 0, but now it's when x1 is 0 and when x2 is 0, so it's doubly conditional. And each predictor would need to be centered if 0 wasn't already meaningful, so that the intercept would be within the scope of the data. So the slope of x1, rather than saying it's the effect of x1 on y, we would have to add in the conditionality of the fact that it's competing with x2 to try and explain this same variable. So I would say that the slope of x1, mathematically still the same. It is the change in y per unit change in x, but it is the unique change in y for a 1 unit change in x. And so you will see people use one of these phrases. There's probably more, but these are the ones that are most common. Controlling for, or partialing out, or holding constant. All of those phrases, to me at least, mean the exact same thing.